Um, let's start with the heat capacity of ideal gas. Okay, so we define heat capacity of ideal gas in simple word as amount of heat required to reach the temperature by 1 degree Celsius, okay, by 1 degree Celsius of unit substance. Unit substance. So this definition, in this definition, we are defining the specific heat capacity. Okay. So you can write in the form of equation as C equals dq over mass times change in temperature. Okay. So here the symbol C I used here is for the specific heat capacity. Here M is the mass of the substance. Okay, so delta T is the temperature change. Okay, so we know based on that the unit of a specific heat capacity is joule per kilogram per degree Celsius or joule per mole per degree Celsius. Okay, so this is the generalized definition of the any substance. But one thing I need to consider here is that in this vessel, you see, we have two vessels. We have vessel 1. In vessel 1, we have um, uh, we have the volume fixed because piston is set at that position means here volume is constant. Okay, and in the cylinder means the piston of the cylinder could move up or could down. So in this case volume will change, but here pressure is constant. Okay, so this means in this example we are talking to a special scenario. Here the pressure is constant but volume will change. Okay, in this case volume constant but the pressure will change. Okay, so the main point of talking this part is that in the case of gas, for gas, the value of C could change from 0 to infinite. So when it is 0, when we are not supplying any heat, then we are not supplying any heat, but there could be the change of T. So for example, you can consider the case in adiabatic scenario, we are not supplying any heat. So dq will be 0, but your change in temperature is not equal to 0. In this scenario, we can say the specific heat capacity of gas will be 0. Okay. If we take the same gas Okay, if you take the same gas, in the case of the isothermal situation, say we are supplying the heat, so dq is not equal to 0, but in isothermal, you know that your change in temperature is equal to 0. So if this is the case, you have the same gas has a specific heat capacity of infinite. Okay, but we know if this is the scenario, this will not give you any result. For that reason, the most important two part we consider means either we have to keep the volume constant or we have to keep the pressure constant to define the specific heat capacity for gas. Okay, so for the gas we generally use two specific heat capacity Cp. So for example, this is the specific heat capacity at constant pressure. This means the scenario is like this. We are supplying the heat so that in this scenario, its volume will increase. Okay, the piston could go up. This is the piston. So there is a change in volume. This part will be the change in volume of the gas. Change in volume. Okay. And the heat supplied will be dq. Then if you keep the its volume is changing, means its temperature will also change. Okay, the other scenario will be we are keeping the volume constant, so we call it a specific heat capacity at constant volume. Okay, so this means in this scenario piston is fixed, piston is not moving, just like here. In the previous case, piston is moving. Here, piston is fixed, so volume of the gas is fixed. So we don't have change in volume. But in this case, we do have change in P. Okay, so here I would write change in P will be 0, but there will be change in P. But in previous case, change in P is not equal to 0, but change in P is equal to 0. So we generally consider two situations when the pressure of the system can be kept constant or volume of the gas is kept constant. Okay, so for a given gas, maybe oxygen, hydrogen, or any gas, for a given gas, this ratio Cp over Cv is constant. Okay, it depends on gas to gas, so it will be, say, value of this ratio is called represented by this symbol. Okay, so let's find the relation between Cp and Cv. How we can find now? Okay, so we want to prove what is the relation between Cp and Cv for ideal gas. If we take the molar gas, then Cp, we want to prove Cp minus Cv is always equals to R. Okay, so let's start with the first law. So first law of thermodynamics, we are using this. So I can write dq equals du plus dw. Okay, say we start with one situation, either at constant pressure or constant volume. So let's start with constant volume. So at constant volume, then then you know this work done will be 0 because work done is equal to P times dV. If we have constant volume, then dV will be 0, so P times 0 will be 0. So in this situation, we have the total supplied total heat supplied heat will be used to change in internal energy of the system. Okay, so we know that as before in previous chapter we defined amount of heat supplied is equal to MC and we can write say change in temperature delta T or dt. Okay, so this is the definition. Amount of heat supplied, Q is equal to MC change in temperature. So in this case, if we use the same equation for if we take the N mole, so we can write N, okay, CV, because this is the case at constant volume, so the specific capacity will be CV to indicate the difference and change in temperature. Okay, so this will be du. So we can use this concept here. So this du is basically the change in internal energy, change in internal energy. Here dt is the change in temperature. Okay, this Cv is the specific heat at constant volume, and in this equation N is the number of mole, how many mole of gas we have taken in the cylinder. So in this situation, our cylinder is this, we are keeping this cylinder fixed, okay, then we are heating at constant volume, so all the heat supplied will be used to get the internal energy. Okay, now let's start with at constant pressure. So let's start at constant pressure, but we want same temperature change dt. Okay, so we start with again with the first law. It is dq equals du plus dw. Okay, this now we are heating at constant, keeping the pressure constant. Okay, so pressure constant happens, then we'll have is N Cp dt. Okay, then we can write du plus pdv. Okay, we know before that the internal energy means in this case du depends only on the temperature. Okay, so in this case also our change in temperature is same. If change in temperature is same, change in internal energy will also be the same. So in previous case, we figure out that change in internal energy is NCV dt. Okay, so I can write this as NCP dt equals NCV dt plus pdv. Okay, so let's say This equation is 1. Our goal is to solve this, okay, to find the relation. So now start, since we know that for the, if we take the n mole of gas, PV is equal to nRT, okay. Now you know that I'm going to differentiate differentiate, so it will be P dV plus V dP equals n is constant, r is constant, dt. Okay, so in this case you know that dP is equal to 0, change in pressure, because this is the case at constant pressure, because at constant pressure change in pressure will be 0, because we are in a situation like this. Okay, if this is the case, then I can write P dV equals n r dt. So this will be the equation 2. Okay, so I write as a note that in mathematics, if dxy, then we can write x dy plus y dx. Same situation is here at the top. Okay, so we can combine equation 1 and 2. So instead of pdv, I can write nr dt. Okay, so let's start with that. So I can write as n cp dt plus n cv dt and ncv dt. Let's say what I have, pdv is equal to nr dt. So I will write here this equals ncp dt equals ncv dt plus pdv will be replaced by nrdt. Okay, so nrdt. So this means for both sides we have this is common, n is here, n is here, n is here, dt and dt will be in the every side, both sides. So we can write this as cp equals cv plus r. Okay, so this means cp minus cv equal to r if you measure the mass in mole. So these are also called molar specific heat capacity, because we started with gas in mole, so these are also called molar specific heat capacity. Okay, so this is also called molar specific capacity at constant pressure, and it is also cv is also called, in this situation it will be called molar specific heat capacity at constant volume. Okay, so as before, this ratio is called the gamma. Gamma is the ratio of cp and cv. So this ratio gamma depends on for the which kind of gas we are taking. So for example, for the one atomic gas, the value of gamma is different for if you take the gas is the diatomic gas. For these gases, the value of gamma is different. The ratio of specific heat capacities will be different. Okay, let's start with for the adiabatic process. So this is just example how this adiabatic process happens. Means in adiabatic process, amount of heat supplied will be zero. We are not supplying any heat, no supply of heat. No supply of heat to the system. Okay, so this means that's why if our system is this cylinder with a piston, this is our system. If this is the case of system, then to stop from the heat loss, we have to put some insulating coat. So these are the insulating coat so that the heat will not come inside from the part, from any part. Okay. So in this process, if we are in the adiabatic process, we have to increase or decrease the um, force and the pressure very slowly. That's why the gas expands, or sometimes it gas could be compressed. Is the adiabatically, and is called the quasi statically in the insulated vessel. Okay, so let's start with how much work will be done in the adiabatic process. So say we have the system as before is like this. So we have this cylinder with a piston. It is it is a closed system. Okay, and this is the process of this is the adiabatic process. So our dq will be zero. So we are not supplying any heat to the system, but the at the initial position could be this one, and the gas expands, and the piston moves up to this position. This is the final position of piston. Okay, final position of the piston. So piston will move from position A to the position B. So here A is the initial position of piston, okay, and B is the final position of piston. But in this is the process, this is the adiabatic process, so no heat enters or leaves the system. Okay, so let's start with our original equation of the first law is dq equals du plus dw. Okay, so this du will be zero for this process, this in this adiabatic process. So we are left with 0 equals, so we know that du internal energy is n cv dt, we showed before, and we have this. This is the dw. Okay, so this n cv dt is true for n mole of gas. N mole of gas. Okay, so let's do some math over here. So I can write dw equals minus n cv dt. Okay, so you know dw is p dv equals minus n cv dt. Okay, so we know that pressure is not constant, so just we need to do a little bit math. So we play with ideal gas equation. So you know that in ideal gas, PV equals to nRT. So P equals nRT over V. So I'm going to replace this P by nRT over V and dV. Okay, so equals minus n cv dt. Okay, and let's see, we can do a little some math over here. So I can write here like this: n r dv over v, and we can write minus n cv dt. Okay, this is same as the previous equation. Next, I'm going to rearrange this equation. dt over t equals dt over t. Okay, dt over t. Just going to rearrange that, so it will be n cv dt. So I need to write here t also, so I forgot that. So dt over t equals, it goes to minus nr over n cv. Okay, and dv over v, this n cancel out. Okay, so I can write dt over t, and this will be minus, this will be minus. Let's find what you mean by r over c. Okay, so we know, we did before, that cp minus cv equals to r. So I'm going to divide both sides by cv. Okay, so r over cv. So cp minus cv is, we can replace by gamma minus 1 equals r over cp. So on that, I can replace r over cb by gamma minus 1, and it is dv over v. Okay. Next, we can we can do integration. Okay, so I'm doing integration dt over t. I take this to that side, so gamma minus 1 dv over v. So integrate. Okay, so I'm doing integration to the both sides. So you know that this is log t, okay, plus gamma is constant, so gamma minus 1 will also be constant. So this gives you log p. So you know that this is a constant. Of any constant will be in integration. If we do, this side will be constant, because we have there is 0. So this is constant, so we can replace this constant by any suitable quantity. So we can write log k. So this k is again constant, some constant. Okay, we don't know its number value. So if this is the case, I'm going to rearrange as log t p gamma minus 1 equals log k. If this is the case, you know that we can write t p gamma minus 1 equals something constant. This is k is constant. Okay, so this is one of the important results in this process, in this adiabatic process. So this gives the information that if we have initial temperature T1, volume V1, gamma minus 1, the final state is T2, volume is V2, we can write gamma minus 1. So we can keep going like this. Okay. So we can find the other set of equation based on that equals to nRT. So this means we can write T equals PV over NR, right? So let's copy the equation that we did before. See, it will be T V gamma minus 1 is basically constant. Let's replace this T by that. So it will be P V over N times R, and V gamma minus 1 equals constant. Okay, so we can write P, this is V, okay, V gamma, we can combine these two, this V and v gamma minus 1. So gamma, so you know n is constant, r is constant, so that's if you take to other side, it will be also constant. Okay, so based on that, we prove pv gamma is equal to constant. So this gives the information is this. We can write p1, the v1 gamma minus 1 will be equal to p2 v2 gamma minus 1. Okay, so again, we can play with the same starting equation. So we start with t v gamma minus 1 equals constant. So let's start with pv is equal to nRT. So our volume v will be nRT over p. So if I plug here, you get t v is equal to nRT over p gamma minus 1 equals to constant. Okay, so we can write t over p gamma minus 1. We can take the other side, other constant to the other sides. It will be constant. We can write n gamma minus 1 r gamma minus 1. So this will be the all constant. So we can write t gamma, okay, t gamma p 1 minus gamma equals constant. So this gives, again, the concept is this. If this is the case, we can also write T1 gamma P1 1 minus gamma must be equals to T2 P2 1 minus gamma. Okay, so we can keep going just like this as before. Now we can come to our actual questions. Our actual question is this: how to find the work done in this process, okay, in the adiabatic process. So let's start. So let's start here, work done in adiabatic. Okay, so we know work done is PdV, okay, integral. So in this case, P, V, and T all are changing, but in our equation we have PdV. So start with volume. Initial volume is V1, final volume is V2. So we can write constant K over VR is equal to dV. Okay, so that's how, because in the process, in this equation, in adiabatic, for this case, we have PV gamma equals to constant. So P equals, say this constant is K over P gamma. So that's how we replaced P of this equation by this number. Okay, so let's go and play with that. So you'll find that when we gauge the constant, so it come outside the equation. So it will be V1 to V2 V minus gamma minus V minus gamma dB. So this will give you K. So this will be P. This will be gamma P minus gamma plus 1 minus gamma plus 1. So it will go from volume changes from V1 to V2. So we can write this as this. We can write this as. Sorry, this is the not gamma. This is the K. Okay, so we can write K minus gamma plus 1. We can write V2 minus gamma plus 1 minus P1 minus gamma plus 1. Okay, we are doing this part. Let's play with this. So I'm writing this as K times V2 minus gamma plus 1. I'm just keeping this K inside, minus K P1 minus gamma plus 1 over minus gamma plus 1. Okay, so we can play a little bit. So you know, in this, in the adiabatic, p1 gamma equals p2 gamma equals to constant. Okay, so we can replace this k and this k by that. Okay, so now I'm going to replace by that. So k will be replaced by p1 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 sorry p2 v2 v2 p2 v2 gamma, this k, and we have still already v2, so minus gamma plus 1. So again k is replaced by p1 gamma, and I have already p1 minus gamma plus 1 over minus gamma plus 1. Okay, so if we simplify that, you will get this will be p2 minus p1. So basically I'm simplifying this equation as far as possible. Okay, let's do more. Let's do the more simplification here. uh, uh, let's do the further simplification. So we know for ideal gas, P1 P1 equals nRT1, and P2 will be equal to nRT2. So we can replace P1 and P2 by nRT1 and nRT2. Okay, so let's replace that. So we'll get work done will be equals to nRT2 minus nRT1 over minus gamma plus 1. Okay, so we can write this as nRT2 minus T1 minus negative gamma plus 1 is the work done. Okay, so we can write that as nr, I'm flipping t2 minus t1 to t1 minus t2. If you flip that, I'm also flipping here gamma minus 1. So this is the equation to find the work done in this process. Okay, so in this way, we can find the total work done in these situations. So you can try with other approach. We can reach at the same approach by the another approach to find the total work done. What we can do is that we start with first law, dq equals du plus dw. So dw is 0 for this process, and that's how we can write dw equals minus du. Okay, so if you integrate to both sides, this is work done w, and minus this is n cpdt d. Okay, so here you can you have this dt, so temperature goes from T1 to T2. So if you do that, minus n cv is constant, you can take out, so you are left with T1 to T2 and dt. So it will also gives n cv T2 minus T1. Okay, so both equations are equivalent. So it depends which equation to use, depends on the what is the question is asking, depending on the given things in the question. Okay, so this said, if you plot a graph for P and V for both process, we are comparing the adiabatic process. and the isothermal process, then you will see that the isothermal curve is not as steep as that for the adiabatic expansion. So you can compare. So you can try yourself and find dp over dv for both. Both means adiabatic and isothermal. Then you will know that isothermal is more steeper than this isothermal. Okay, let's do for the this process, an isobaric process. So isobaric process means in isobaric process we keep the pressure constant. Okay, so let's start our equation. dw is pdv. We can integrate to both sides. Okay, the volume could go from v1 to v2. So this total work done will be W. In isobaric, pressure is constant, so this P will come out from the equation, from this sign, integral sign. So will be like this. So this is the simplest case. You will easily find work done will be equal to P, and if you integrate like this, you will get that P2 minus P1. So for the isobaric process, work done will be just P and change in volume. Okay. For the isochloric process, your V is constant. If V is constant, then you can say that dW equals PdV. So there will be work done with the zero. Okay. If you understand up to this point, you can solve this problem. Okay. So you have to use the equations that you know up to this point. Then you can get the answer for A and B. Okay. So these are the further resources. If you have time, I recommend to watch. Okay, these are the these are the videos that will further help you to understand the concept. Okay.